Hi, in this lesson I am discussing Edexcel IAL January 2022 Unit 5 paper. Okay, we'll go to the first question, MCQ, section A. The first question is about regarding the simple harmonic motion. A mass oscillates with simple harmonic motion about a fixed point O. So it oscillates about a fixed point O means O is the equilibrium position. You know that. Which of the following statements about the motion of the mass is correct? Okay, so briefly I'll describe the simple harmonic motion. So imagine an oscillator, maybe a particle, what I showed by like a sphere, is oscillating between P and Q, and O is the equilibrium position. If I think like that, whenever the particle on the right side of O, the acceleration will be towards the equilibrium position. Always the acceleration will be towards the equilibrium position. That means, according to Newton's second law, the resultant force will be, or the restoring force will be always towards the equilibrium position. So if the particle is here, the oscillator is here, the acceleration will be always towards the equilibrium position. And you must know the displacement is always measured from the equilibrium position. So if the particle is here, the displacement is measured from the equilibrium position, so it will be towards right. When the particle is here, the displacement will be measured from the equilibrium position, that will be this direction. So displacement is always measured from the equilibrium position. So always the direction of the displacement will be away from the equilibrium position. Or I can say always the displacement will be away from O. Always the acceleration will be towards O. Velocity, what happens? The direction of velocity will continuously change depending on the direction of motion. Say, for example, when the oscillator moves from O to Q, the velocity will be towards right, towards Q. But when it is moving from Q to O, the velocity will be towards O. So the direction of velocity will continuously change, right? So we learned that in Unit 1, whenever the direction of velocity is along the direction of acceleration. Now, otherwise, if I say whenever the direction of velocity and acceleration are parallel to each other, object will accelerate. So when it moves from Q to O, the object will accelerate because the direction of velocity and the direction of acceleration are parallel to each other. Same way, when the object moves from, or the particle oscillate moves from P to O, the direction of velocity will be towards O, acceleration also towards O, the particle will accelerate. Whenever it moves from O to Q, the velocity is away from O, acceleration is towards O, so the particle will decelerate. Okay, we'll see one by one the statements. First statement, its velocity is always towards O, is wrong statement. We know, I already showed that the direction of the velocity will continuously change depending on the direction of motion. The acceleration, second statement, its acceleration is always towards O. Yes, I already showed that acceleration is always towards O, the equilibrium position. So that is the correct statement. Anyway, we'll check the C and D also. Answer C, its acceleration is directly proportional to its velocity. No, acceleration is directly proportional to displacement. That is the condition for simple harmonic motion. So answer C is wrong. Answer D, its acceleration and its velocity are always in opposite to each other. No, that is wrong. Acceleration and velocity are not always opposite to each other. You know, I already showed that when it moves from Q to O, the acceleration and the velocity are parallel to each other. But remember that always the direction of acceleration and direction of displacement are opposite to each other. So answer D also a wrong statement. So the correct statement is B. So question number 1, correct answer B. Okay, second question. In an experiment to determine the specific heat capacity of vaporization of water, LV, a student used an electrical heater to boil water in a beaker. The experimental data gave the rate heat of vaporization is given. The textbook value is 2.26 10 to the power, 2.26 megajoule per kilogram, but the value obtained by the student through experiment is 2.20 megajoule per kilogram. That means a student is getting a lower value than the actual value. The actual value is the value given in the book, which is more than the value obtained by the student. Which of the following could be an explanation for this difference in the value of LV. So we know the equation. How can we use? If the power of the heater he used is P into T, that is the energy given by the heater, is equal to the equation for latent heat of vaporization is delta M, the mass vaporized, times LV. So LV will be equal to P into T over delta M. So delta M is the mass vaporized during the boiling. So a delta M is the mass vaporized, T is the power of the heater, T is the time take, LV is the latent heat of vaporization. So the first statement, some energy is transferred to the surrounding. Okay, so if the energy is transferred to the surrounding, what happened? The power of the heater remains constant. So imagine the power of the heater is fixed, not changing. It remains constant. If the uh, some energy is lost to surrounding means it will take more time. So the student is measuring maybe, for example, 10 minutes. So the 10 minutes is including the time taken to lose heat to the surrounding also. So in there he will get a value LV more than the actual value. So if there's heat loss to surrounding, that means it will take longer time. Practically, he will take longer time than the actual time. See, because heat is lost to the surrounding. So he will take longer time than the actual time. Means he will get a value which is more than the actual value. But the question is, he got a lower value than the actual value. So answer A is not correct. Statement B, the heater power was underestimated. Yes, actually the power of the heater may be 500 watts. The student would have thought it is 400 watts. So he got the time, actual time for 500 watts, right? Actual time for 500 watts because heater is working at 500 watts. But the student thought he's measuring the time, is it? For the certain mass, known mass to vaporize, the time is measured. So there is no mistake in the measurement of time, measurement of delta, no mistake, those are correct. But he is substituting a lower value for P because he underestimated the power of the heater. So there he will get a lower value for LV in his experimental results. So the correct answer is B. We will check the answer C also. The student did not stir water. Yeah, that's nothing related. So, because when it starts vaporize, we'll assume the heat is uniformly distributed. So if it is not stirred, the heat will not be supplied equally. So there the time taken will be more, then he will get more larger value than actual value. So answer C also wrong. Heater is inefficient. Inefficient means the heat supplied by the power supplied by the heater is lower than the value marked on the heater. Maybe heater might be showing 500 watts, but it's going to supply only 400 watts, means the time taken will be longer than the actual value, is it? So there he will get a larger value. So the correct answer is B. Question number 2, correct answer B. Okay, question number 3. In the Pendulum in Paris, there is a pendulum that takes 8.25 seconds to swing from one extreme position to the other. So the time taken to swing from one extreme position to the other means, if it's the pendulum, if it swings from here to here means the time taken will be half the period. You know, one full oscillation, the time taken for one full oscillation is the time period. So one full oscillation means if you start from extreme position, one full oscillation means it should go from here to here, then back to here. The time taken for this oscillation is one period. But here it's moving from one extreme position to the other extreme position. So the time taken will be half the period. So the half the period is given as 8.25 seconds. As 8.25 seconds is half the period. So T will be 2 times 8.25 seconds. Okay, which of the following expressions gives the length of the pendulum? So we know the equation for simple pendulum. This is question number 3. So we know that T equal 2 pi square root of L over G. So the T will be 2 times 8.25. So 2 into 8.25 is equal to, that is, 2 into 8.25 will be equal to 16.5. I'll do that. 2 pi square root of L over G. So that is 16.5 equal 2 pi square root of L over G. We need to find the L, so square the both sides. 16.5 squared equal 4 pi squared times L over G. So L will be equal to 16.5 squared cross multiply G 9.81 over 4 pi squared. So the answer correct one is D. Correct answer D for question number 3. Okay, question number 4 related to radioactivity. Tritium is a radioactive isotope. Wine may contain traces of tritium. One 25-year-old bottle of wine was found to have an unusually high activity of 22 becquerel. Half-life of tritium 12.5 years. Which of the following gives the activity of this wine when it was bottled? Okay, so we know the half-life. So we can use the equation T half is equal. First, we need to find the decay constant. So T half is equal to ln2 over lambda. So lambda make the subject. So ln2 over T half is given as 12.5 years. I can keep it in 12.5 years. So I'll get the lambda in per year. So that will be 0.055 per year. I can keep value of lambda anything whether per second or per day or per year, anything I can keep it. So, but when you are using A equal lambda n, careful, when you are using A equal lambda n, their lambda must be in per second. You can't keep any other units for lambda because you know activity, the unit is becquerel, becquerel means per second. So here n has no unit, lambda must be in per second, then you will get activity per second, that is becquerel. So their lambda must be kept in per second. But if I am going to use any other equation, A equal A naught e to the power minus lambda t or n equal n naught e to the power minus lambda t, I can keep lambda in any unit. It's not necessary to keep in per second, right? So here I'm going to use A equal A naught e to the power minus lambda t. So we know the activity. Now, the current activity we know that is 22 becquerel. So, how much it was 25 years ago? That A naught, I need to find A naught, sorry, A naught into e to the power lambda, that is minus 0.5, 0.055 into the time is years, 25 years. So remember that always the unit of the exponential quantity must be nothing. Actually, it should not have any unit. So that's why I should say the exponential function should not have any unit. So if I keep this in per year, the time should be in year. If I keep this in per day, time should be in day. So it should tally the same type of units for lambda and t, right? So now solve it. A naught is equal to 22 over e to the power minus 0.055 into 25. Solve it. The value will be almost 87.8 or something. You can say 88. So the correct answer is C for question number 4. Okay, question number 5. A fixed mass of an ideal gas has a volume V and exerts a pressure P. The absolute temperature of the gas, you know, absolute temperature means temperature in Kelvin scale, is T. When the gas is heated, the new pressure is 4P. Which row of the table gives correct value for the new volume and the new temperature? So here all three quantities are changing. Pressure, volume, temperature, all three are changing. So we can't use Boyle's law because Boyle's law, their temperature must be constant. We can't use pressure law, their volume must be constant. We can't use Charles law, their pressure must be constant. So here all three are changing means we can use combined gas equation, that is PV over T is constant. So PV over T is constant. That means we can say P1 V1 over T1 equal P2 V2 over T2, that is combined gas equation. So here we know the initial pressure P, initial volume V, and the initial temperature T. Now it is changed. What are the changes they are causing? The new pressure is 4P times. Now 4P times. Now V2 over T2. So V2 over T2 should become V over T. So sorry, V2 over T2 should become 1 over 4 to get the same format. So we'll check one by one. So first answer, volume becomes V by 2 and the temperature becomes 2T. So when the volume becomes V by 2, what will happen? So 4P times V by 2 over 2T is it first answer. So this 2 goes down. So it will become V over 4T. That 4 and this 4 will get cancelled. We will get PV over T. So this and this are becoming equal. Is it? So correct answer is A. If you substitute the other one, V, the answer B, that it says V by 2 and 40. So V by 2 and 40. So there if you solve, it will become uh, PV over 2T. So PV over 2T is not equal to PV over T. So that is not tallying with the combined gas equation. So like that, if you substitute other answers also, it will not tally and will not give this answer what you got on the left side. Okay. So the correct answer, if you substitute, it should be answer A. That is 2T. So 2 comes down 4T. So it will become PV over T. So initially and finally, the ratio PV over T remains constant. So the correct answer for question number 5 is A. Okay, question number 6. Current theory suggests that the universe is expanding. Which of the following is evidence to support this theory? Okay, you know the evidence for uh, universe is expanding. What are the evidence? First answer, all galaxies appear to be rotating in space. Yeah, but it's not nothing related to it. Actually spiraling. About the central of the galaxy will be most of the galaxies have black hole and they are spiraling, but that is nothing related to expansion of the universe. So answer A is nothing related to that expansion of the universe. Answer B, dark matter has been detected in the universe. No, the dark matter is nothing related to expansion of the universe, but dark energy, if they say something we can accept, whenever universe expands, the space is filled with dark energy. So the dark energy is the reason for acceleration of the galaxies when they are receding from us. According to Hubble's law, when they move away and away, their speed is increasing, means they are accelerating. Why are they accelerating? Due to the energy given by the dark energy. So if they say dark energy, somewhat we can accept, but dark matter is nothing related to expansion of the universe. So statement B also not acceptable. Answer C, all distant stars are observed to be increasing in size. Stars are not increasing. The size of the stars are not increasing. So anyway, answer C also not acceptable. So A, B, C, all three are wrong, means we know the D. The further a galaxy is from Earth, faster it recedes. Yeah, that is the Hubble's law. So why are they receding? Increasing speed. They are moving away from us. Universe is expanding. Why are they accelerating or the speed is increasing? That is due to dark energy. So question number 6, the correct answer D. Question number 7, a student investigates the absorption of gamma radiation by lead. She determines the background radiation count rate before she starts the investigation. So we don't need to think about absorption, but here about background count rate. So the question is based on background count rate, measurement of background count rate. So which of the following would not affect her value for the background count rate? So that's the question. This is related to measurement of background count rate. First statement, the place where she made the measurements, that certainly will affect depending on the positions or locations of on earth. The background count rate can change because the deposits in the soil can be different in different part of the world. So certainly that will affect the background count rate. So the question is, which of the following would not affect? So answer A is not correct. Answer B, the temperature of the surrounding. Temperature does not, radioactivity is a spontaneous emission. Spontaneous emission means it does not depend on external factors like pressure, temperature. Those things will not affect the radioactivity. So answer B also not correct. Answer C, the time interval for background count rate. Actually, sorry, I made a mistake. Which of the following would not affect means yes, temperature. Temperature will not affect. Yeah. So the question is about which one will not affect. So temperature will not affect because the radioactivity decay is a spontaneous emission. So A will affect. I already told that. B will not affect. That the temperature won't affect because it's a spontaneous emission. C, the time interval for the background count rate. Yes, you know the background count rate is random. So if you measure background count rate for maybe just 2 seconds, it might be 0. If you measure for 5 seconds, it might be little more. If you measure for 10 seconds, it will be more. So normally what we say, when you are measuring background count rate, measure reasonably longer time, something like 15 minutes, and find the count rate. So time interval for measurement of background count rate will affect the measurement of background count rate. So answer C also not correct because the question is which one will not affect. So answer C, time will affect the background count rate. Uh, D, the type of radiation detector she used. Yeah, the different type of radiation detectors, their sensitivity might be different. So due to the sensitivity of the detectors, that also will give uh, different count rates depending on the sensitivity of the instrument you are using. So which one will not affect? Temperature will not affect because it is a spontaneous emission. So question number 7, correct answer is B. Okay, question number 8. Sirius and Alpha Centauri are two of our closest stars. Sirius has a luminosity about 16 times greater than the luminosity of Alpha Centauri. Sirius is twice as far away from the Earth as Alpha Centauri. The intensity of light from the Sirius is IS, and the intensity of light from Alpha Centauri is I alpha. Which of the following is the value of IS over I alpha? So you know the equation, the intensity and the luminosity are related by question number 8 are related by I equal L over 4 pi d squared. So we can say IS and I alpha ratio we need to find. So I can divide IS over I alpha. So when I divide, 4 pi will get cancelled. So it will become LS over divided. Max IS, I can write separately IS equal to LS over. I can say IS is equal to LS over 4 pi ds squared. Same I can say I alpha equal L alpha over 4 pi d alpha squared. So I can say this is equation 1, this is equation 2. So I need to find I s over I alpha means 1 over 2, equation 1 divided by equation 2 will give. So this will be L s over L alpha. So when you divide this one over this one, Ls over L alpha, this will go up. So that will become d alpha over ds all the squared. So 1 minute, I'll write below that. So Is over I alpha equal d alpha Ls over L alpha into d alpha over ds all the squared. So here it's mentioned that is the luminosity of the Sirius is 16 times greater than the luminosity of alpha. So Ls over L alpha is 16. And also it's mentioned the distance is the distance of ds is twice the distance of alpha. It's mentioned that Sirius is twice as far away from the Earth as Alpha Centauri. So that will be the alpha over ds will be half all length squared. So that will be 4. So that will be 4. So Is over I alpha will be 4. So the correct answer, question number 8, is B. Okay, question number 9. The spectrum of electromagnetic radiation from a galaxy is observed to have redshift. Which of the following is a correct statement about lines in the spectrum. So you know that when you think about redshift, a closest galaxy, the light from the closest galaxy, if the spectral lines, this is a violet, this is the red. So if it has a spectral lines like this is a line of spectrum from the closest galaxy, or we can say these are the absorption lines. From faraway galaxy, the same lines will be observed shifted towards red color. The lines will be shifted towards. So this line will appear here. This will appear here. The double line will appear here. So you can see they'll be shifted towards red color. They will not become red. They'll be shifted towards red color. So first statement, all the lines are in the red part of the spectrum. No, they won't be in the red part, but they can shift towards red color. So they won't become red. So answer A, statement A is not correct. Statement B, all the lines are observed to have longer wavelength. You know, red color has longer wavelength than violet color. So they all, compared to this one here, all the spectrum lines will have longer wavelength than expected. So that is the correct statement. We'll go to the C. Lines with wavelengths at the red end of the spectrum are not most intense. So nothing related to intensity here. So answer C is not correct. Light of all the lines was emitted with longer wave. No, they are not emitted with longer wave. Actually, the light from the uh, faraway galaxy or light from the nearby galaxy, the wavelength emitted are the same. There's nothing different. The wavelength emitted is the same, but due to relative motion, when we observe, we will receive wavelength with larger value if the galaxy is far away. So they are not emitting larger wavelength. That statement is wrong. They are emitting the actual wavelength. Far away galaxy and nearby galaxy both are emitting almost the same, or exactly the same wavelength, but faraway galaxy is moving away from us. So due to relative motion between us and the faraway galaxy, we will receive the wavelength we receive will have larger wavelength. Careful, don't say they are emitting larger wavelength. This is a wrong statement. So that's the reason statement D also not correct. So question number 9, correct answer B. Okay, question number 10. The graph shows how the binding energy per nucleon depends upon the nucleon number. It's a standard graph you can see anywhere in any textbook. The binding energy per nucleon against nucleon number graph. Which of the following can be deduced from the graph? First statement, iron readily undergoes fission. No, iron will not undergo fission because we know iron is the most stable nucleus. It can undergo fission only when you supply energy. If you supply energy, that can happen, but it won't undergo fission reaction, and it will not emit energy. You supply energy, then you can make it to happen the fission reaction for iron. So the first answer is not correct. Answer B, fission releases less energy than fusion. So that you can't say because the graph shows binding energy per nucleon, not the binding energy. So the difference of the binding energies is the amount of energy released. When you think about the way we calculate binding energy difference can give the energy release, but here they are giving the binding energy per nucleon, not the binding energy. So answer B also not correct. So for example, if you think about the graph, if it is something like this, so if you think about fusion, a nucleus from here, two nucleus are forming and giving out here, the difference can give the energy release. But here, this is not. Now here the slope is more, slope is less. Slope is less means the difference between the initial and the final can be small, so we can say energy release is less. But here we can't calculate it because here they are giving the binding energy per nucleon, not the binding energy. So by using the graph, we won't be able to calculate the energy release during fission or fusion reaction, because the graph is telling about binding energy per nucleon, right? So that statement also wrong. Answer C, high mass nuclei cannot undergo fusion reaction. So there, that statement is not correct because I already told you can make it to happen by supplying energy. If you give energy, that can happen. So for example, during supernova, now you know all the massive stars, when their lifespan, they can go up to, or they can fuse until iron is formed. But the theory says how we got on Earth, there are elements beyond iron also. How are they created? So during supernova, one of the theories says during supernova, you know, the huge amount of energy released during that explosion, that energy fuse beyond iron also. So by supplying energy, you can make any element to undergo fusion reaction, right? So answer C also not correct. Answer D, low mass nuclei release energy during fusion. Yes, normally they release energy. Low mass nuclei, they undergo fusion reaction, so they will produce element with larger mass somewhere here. So here, low mass can form helium. Say hydrogen can form helium. So binding energy per nucleon of the helium is more than binding energy per nucleon of the hydrogen, means you know the product is more stable. So energy will be released. Remember that whenever a product is more stable than the initial elements or initial nuclei, energy will be released. If the product is unstable, then you need to supply energy for that reaction to happen. So remember those things. So question number 10, correct answer D. Low mass stars undergo fusion and they release energy. The reason, the product is more stable than the initial element. So more stable, how do I know? Its binding energy per nucleon is higher, the product. So it will release energy. So question number 10, correct answer D. Okay, question number 11, that is related to simple harmonic motion. A graph is given. A mass is hung from a spring and set into vertical oscillation by displacing the mass 5 centimeter from its equilibrium position. The graph shows how the acceleration A of the mass depends upon the displacement x. You know, normally acceleration against displacement graph will be a straight line through the origin. So you know that A equal minus omega squared x. X is the displacement measured from the equilibrium position. If you plot a graph of acceleration against displacement, you will get a straight line through the origin like this. So this is the acceleration, this is the displacement. You get this straight line through the origin. This will be the amplitude minus A, and A you can read it from the graph. This is the accelerations, maximum and minimum, opposite direction, maximum acceleration. So the gradient of the graph will be equal to omega squared. So they gave the graph and asked sketch a graph on the axis below to show how the displacement depends upon the time. So we know the displacement time graph will be, if we think about x equal a sine omega t, it's a sine graph. But we need to show the values. What are the values we need to show? We need to show the time period and the maximum displacement. Maximum displacement, we can get it from the graph, that is 5 centimeter. And this is minus 5. Those are the maximum displacements. We can get it from the graph. So we need to find the time period. So use the graph, find the gradient of the graph. Gradient is equal to, find it from the graph. So that will be equal to omega squared. So that will be, I took minus 8 minus 0. You can see those values. Minus 8 minus 0 over, that is minus omega squared is the gradient. So over 5 minus 0. So omega squared is going to be 5 over 8, 8 over 5, that is 1.6. So we know that, take the square root of it, and also we know that omega equal 2 pi over t. So substitute, find the omega value and substitute omega equal 2 pi over t. You will get 2 pi over t is equal to 1.265. From that, find the period. That will be 4.97. I can take it approximate to 5 seconds. So I know the period of the graph. So now I need to sketch displacement time graph. It's a sine graph because normally we give x equal a sine omega t. So when t equals 0, displacement 0, you can draw a graph for two full oscillations. So there you can see my graph little bit. It's okay. 0, this is the time period. You can say 5, this is 10. 10 seconds. So the amplitudes 5 minus 5. That's the answer for this question. Okay, question number 12 related to thermal physics. Cocoa powder, milk, and hot water are mixed together to produce a hot chocolate drink. The mass of the drink is 275 grams and its initial temperature 71.5 degrees Celsius. So when it is made, its temperature is 71.5 degrees Celsius. Ice at 0 degrees Celsius is added to the drink to reduce its temperature. Research indicates that the maximum serving temperature of any hot drink should be 58. So when you make the drink, it is at 71.5 degrees Celsius. You need to reduce its temperature to 58 degrees Celsius by adding some ice. You know, when you put ice, ice will melt. When ice melts, they are putting it 4 gram of ice which is at 0 degrees Celsius. We should take it's at melting point. So if you add that melting point is not given, they didn't say anything about melting ice or ice at 0 degrees Celsius. Ice can be at negative temperature also, but here in the data they did not say anything about the specific heat capacity of ice. So we should assume the ice initially at 0 degrees Celsius. When you add 4 gram of ice into that chocolate drink, ice will melt. So we can use latent heat of fusion. So ice will melt and absorb heat from the chocolate drink. Then ice will become water at 0 degrees Celsius. Then that water also will absorb heat from the chocolate drink. Finally, the chocolate drink and the ice which becomes water, they all will be at the same steady final temperature. That should be 58 degrees Celsius. But the question is, deduce whether 4 gram of ice would be enough to bring the temperature below 58 degrees Celsius. So they are giving specific latent heat of ice, that is latent heat of fusion of ice. Specific heat capacity of hot chocolate drink is given. Specific capacity of water, all are given. So we need to find out whether the 4 gram of ice can bring the temperature of the chocolate drink from 71.5 degrees Celsius to 58 degrees Celsius. So that's the thing we need to find. Okay, so this can be done in two different ways. First method, I can find like this. Okay, I'll assume the final temperature becomes 58 degrees Celsius. How much of ice I want? What mass of ice I want or I required, or what mass of ice should be added to the hot chocolate drink, which is at 71.5 degrees Celsius, to bring it to 58 degrees Celsius. What mass of ice should I add? I can find the mass and compare that mass with 4 gram and conclude the answer, whether it's 4 grams enough or not. The other one, you can assume you are adding 4 gram of 4 gram mass of ice as 0 degrees Celsius, and what could be the final temperature, whether the final temperature becomes 58 degrees Celsius. Anyway, whatever the approach you do, the question, the way we answer depends on conservation of energy. I can say heat lost by chocolate drink is equal to heat absorbed by ice when it melts. You know, when it melts, it will become water at 0 degrees Celsius. Then it will absorb further heat from the hot chocolate drink until the temperature of the ice water, which is at 0 degrees Celsius, which is obtained from the melted ice, to become the final steady temperature T. Right? So we'll do method 1, method 2, both methods I will do. So question number 12, method 1. So here I'm adding 4 grams of ice and I'm going to check what will be the final temperature. We assume there is no heat loss to surrounding. So the container or the cup or whatever it is fully thermally insulated, right? So I can say here heat lost by hot ice or heat lost by hot chocolate drink equal heat absorbed by ice when melts. First it will melt. I assume the ice is at 0 degrees Celsius. That is not mentioned in the question, but we assume the ice is at 0 degrees Celsius. So the first ice will melt and it will become water at 0 degrees Celsius. So then that water also will absorb heat. So I can say heat absorbed by ice water. We are not adding ice water. This ice water is from the melted ice. Okay, so we know the heat lost by the hot chocolate drink. I can say mc delta T, mass of the chocolate drink, specific capacity of the chocolate drink. Initially, it is at a temperature of 71.5 degrees Celsius. Finally, it should become T. So I'm going to find the final temperature because in this one, I am assuming we are adding 4 grams. Is it enough to get the final temperature of 58? We'll see what's the final temperature. So final temperature is T. I'm going to find it, right? Equal to heat absorbed by the ice when it melts. So that is delta M of ice times latent heat of fusion of ice plus heat absorbed by ice water. The same mass of ice will become ice water. So that will be delta M C ice, specific capacity of water, sorry, that is specific capacity of water. This ice mass, same mass. So specific capacity of water, the same delta M, because the same mass of ice is now in the water format. So that mass of water, which is in the early it was ice, so I can say MW, I can say whatever it is, that MW is equal to delta MI, MW to CW. The final temperature should be T because it's going to be the final temperature minus, initially it was at 0. Okay, we'll substitute the values. Mass of the chocolate is 275, means 0.275. Specific capacity of chocolate is hot chocolate 3750. 71.5 minus T. Mass of the ice is 4 grams, so 4 into 10 to the power minus 3 kilograms. Latent heat of fusion of ice is 4109, 3.34, 10 to the power 5. Mass of water, the same, ice water, 4 into 10 to the power minus 3. Specific capacity of water given 4190 into T minus 0. Okay, solve it and find the final temperature T. So you will get it like this one. When you solve, you will get 737. Yeah, you can solve it, but anyway, step by step I'll solve. 734.4 minus equal. So the other one is 1336. If you solve this one, plus 16.76 T. Okay, now you know how to solve it, the T. So you will get the T, final T, you solve it, you will get 69.1 degrees Celsius. So this temperature is greater than 58 degrees Celsius. So 4 gram of ice is not enough to bring the temperature to 58 degrees Celsius. Okay, so method 2, there I'm going to find how much of mass, what mass of ice is required to bring the final temperature to 58 degrees Celsius from 71.5 degrees Celsius. So same energy equation, conservation of energy. So heat lost by hot chocolate. So the mass of the chocolate mc delta T. So mc Cc delta T, the final temperature, I'm taking 58 degrees Celsius. I'm going to find the mass of the ice here. So the final temperature will be 58 degrees Celsius, 71.5 minus 58 equal. Mass of the ice, I'm going to find it. So I can say the mass of the ice, Mi or delta Mi, whatever I can say, uh, no problem. So Mi times latent heat of fusion, Mi or delta Mi, whatever it is. This is the mass of ice melted to bring the temperature of the hot chocolate from 71.5 to 58. So MILF plus the same mass of ice has become water. So I'll say Mi, now it's in the form of water, CW delta T, MC delta T. So delta T's final temperature is going to be 58 from 0. The water was at 0 after it melts. Finally become 58 degrees Celsius. Okay, I'm going to find the Mi here. So mass of the chocolate is again 275 grams, so 0.275 kilogram. Specific capacity of the chocolate is 3750 into this quantity. So that will be 13.5. Mass of the ice, I am going to find it Mi times latent heat of fusion of ice is 3.34, 10 to the power 5 plus Mi 4190 into 58. I need to find the Mi here. Okay, so when you solve this left side will become this much. Mi. So find the equation, solve it. You will get Mi, the mass of ice required to bring the temperature to 58 from 71.5. You will get 0.024 kilograms. So in grams multiplied by 1000, that will be 24 gram, which is greater than 4 grams. So 4 gram of ice is not enough to bring the temperature from 71.5 to 58 degrees Celsius. Either way you can do. Okay, question number 13. A weather balloon takes scientific equipment high into the atmosphere to monitor atmospheric conditions. So there are the initial pressure, temperature are given, and the volume also given when it is at the ground level. That is given as 22.5 degrees Celsius temperature, and the pressure 1.02 10 to the power 5, that's atmospheric pressure, and the volume 7.5 meter cube. The balloon rises through the atmosphere to a maximum height. At the height, the temperature is minus 48 degrees Celsius at high latitude, and the pressure of the hydrogen at that height is 8.40 10 to the power 4 Pascal. Calculate the volume of the balloon at that height. So here all three macroscopic quantities are changing: pressure, volume, and temperature. So we can't use Boyle's law, pressure law, or even Charles' law, because there we can use whenever there is only one quantity, or like a mass. If it is a Boyle's law, mass and temperature should remain constant. If it's a pressure law, then volume and mass should remain constant. If it's a Charles law, again pressure and mass should remain constant. But here all three quantities, pressure, volume, and temperature, changing. So we need to use combined gas equation, PV over T constant, right? So PV over T constant. So I can use P1 V1 over T1 equal P2 V2 over T2. Careless, common careless mistake. Students won't convert the temperature to Kelvin. It must be Kelvin. The temperature must be. So the initial pressure is I can say P1 V1 over T1 equal P2 V2 over T2. That's the format we normally use. So P1 is 1.02 10 to the power 5. The volume is 7.50 over T1 is we had to convert 22.5 degrees Celsius to Kelvin. So to convert to Kelvin, add 273. So that will become 295.5 equal 8.40 is the pressure into 10 to the power 4 into V2 over the temperature is minus 48 plus 273, 225. Okay, so find the V2. That is the question number 13A part. So the V2 will be 6.93 meter cube. Okay, B part, calculate the decrease in mean kinetic energy of hydrogen molecule of a molecule. So just one molecule in the balloon as the balloon rises to maximum height. You know the average kinetic energy or mean kinetic energy is given by half mc squared equal to 3 by 2 kT. So you know that the temperature is, we don't know anything about the mean square speed, but we know the temperature. So we can say loss in kinetic energy, mean kinetic energy, or decrease in mean kinetic energy of a molecule. So we know that when the temperature drops, mean kinetic energy will decrease. So loss means initial minus final here. That is 3 by 2 K T1. That's the initial temperature minus 3 by 2 K T2. So that I can say 3 by 2 K T1 minus T2. Both should be in Kelvin. The temperatures must be in Kelvin. So that will be 3 by 2 Boltzmann constant K, that is 1.38 10 to the power minus 23 into T1 minus T2 295.5 minus 225. So that will be equal to 1.46 into 10 to the power minus 21 joule. That's the loss in mean kinetic energy. Okay, question number 14 is about a range of alpha particle in a medium. You know, range of alpha particle means, or range of a particle in a medium means the maximum distance the particle that can travel through a medium. So the kinetic energy should become zero when it is completely stopped. So the range, the maximum distance it can travel through a medium is called range. So strontium 90 is commonly used in schools to demonstrate the properties of beta particles. I'm doing question number 14. The range of energies of beta particle. Careful, here the word range of energy. So that is distribution of energy. That is nothing related. Word range is nothing related to range of the particle in a medium. That is, you know, beta particles are emitted with a range of kinetic energy. That means a distribution of kinetic energy. So, but if it is for a given sample, say for example, if it is alpha emission from a radium becomes radon, when that happens, alpha particle will be emitted with just one particular kinetic energy always when it is emitted from a particular radioactive element such as radium. Alpha particle will be emitted with one particular kinetic energy. But if it is a beta decay or emitted, a beta particle is emitted from a radioactive source, the beta particle, even from a particular radioactive element, the beta particle will not be emitted with the same kinetic energy. It will be emitted with a range of kinetic energies because the energy released during beta decay will be shared between beta particle and anti-electron neutrino. So those two particles will share the energy released. So since they are always sharing the energy released, the beta particle can have a range of kinetic energy or distribution of kinetic energy. So the range of energies of beta particles emitted from a source of strontium is shown by this graph. So you can see where it touches the, I don't know, the value is not given, maybe 0 or lowest value. So anyway, so different energy. So you can see uh, number of particles with 0.1 mega electron volt will be this number of particles, with 0.2 this number of particles, like that. A different number of particles emitted with different kinetic energy. And the second graph shows the range of the particle when it travels through a medium, air. The medium is air. So if the kinetic energy is this much, the range will be this much. You can read it from the graph. If the kinetic energy is this much, you can read it from the graph what could be the range in air for that particular kinetic energy of beta particle. So the question is, it is estimated that the most energetic beta particles from strontium-90 will ionize 250 nitrogen molecules per centimeter of air that they pass through, right? 15.6 electron volt is required to ionize the nitrogen molecule. You know, what's the reason for the, say for example, if I say alpha particle, its range is 5 centimeter. What's the reason? Why can't it travel beyond 5 centimeter in air? Means alpha particle. When it passes through air, it will collide with the air molecules, right? And ionize the atoms of the air molecule. So due to ionization, the alpha particle will continuously lose its kinetic energy. So when it travels through 5 centimeter in air, it loses all its kinetic energy. So here they are saying when beta particle travels through air, uh, will ionize 250 nitrogen molecules in 1 centimeter, and the required energy to ionize one nitrogen molecule is 15.6 electron volt. Assess whether this estimate is consistent with the range of these beta particles in air. Okay, so we need to think about high energy beta particles. Most energetic beta particles will ionize 250 nitrogen molecules per centimeter, and they will lose 15.6 electron volt during each collision with nitrogen molecule. So that is the estimate. Assess whether this estimate is consistent with the range of these beta particles in air. Okay, so this question also I can approach in two different ways. Okay, I can take the most energetic beta particle as zero point 0.5 mega electron volt or little more than that, but this value is you can't directly get it from the graph because there are no divisions, subdivisions between zero point 0.5 and zero point 0.6. So I'll just take simplicity. If you want, you can take this as a 0.52 or 0.53 where it cuts the x-axis, but I will take this particular value 0.5. So when you read it from the graph, if I take zero point 0.5 mega electron volt as one of the high energy beta particle, so for zero point 0.5 mega electron volt, I am going to find how many nitrogen molecules will it ionize when it passes through 1 centimeter. So if I take zero point 0.5 beta particles, the high energy, from the second graph, for zero point 0.5, this first method, find for the zero point 0.5 mega electron volt, what is the range I am going to find it? What will be the range? I am going to find it from the graph. So when it find it from the graph, for zero point 0.5 mega electron volt, the range is almost 1.3 meters. From the graph for zero point 0.5 mega electron volt of beta particle, its range is 1.3 meters. So I'm going to find how many number of, that means it is unable to travel beyond 1.3 meters. So during this 1.3 meters, it lost its all energy and it will lose during every collision 15.6 electron volt. How many nitrogens it collide when it travels through 1.3 meters? Then I can find out in 1 centimeter how many nitrogens will be there, and I'll compare with 250. That's the first method. Okay, so here I can see most energetic beta. So this is question number 14. Most energy equals 0.5 mega electron volt. So the range equal 1.3 meters. So let the number of with nitrogen molecules let the number of nitrogen molecules per centimeter equal n. So total number of nitrogen molecules in 1.3 meters in 1.3 meters, that will be equal to n into, that is in 1 centimeter, 1.3 convert to centimeter, 1.3 into 100. So that will be 130 n. So this is the number of collisions it made in 1.3 meter and lost all its energy. We'll see the number of n. So total energy lost by total energy lost by beta minus due to ionization will be equal to 0.5 mega electron volt because it lost all its energy. So we can say n 130 n. That's the total number of nitrogen molecules it collide when it travels through 1.3 meters. During each collision, it lost 15.6 electron volt. That should be equal to mega electron volt. So find n, that will be 247, approximately 250 nitrogen molecules. So the estimation is correct, or the statement is correct. This I can say first method, method 1. I found the number of molecules in 1 centimeter. Okay, so method 2, I'm going to do like this. That's the first method I already discussed. There we found the number of molecules, number of collisions made with nitrogen molecules in 1 centimeter, and it tallies with 250. We got 247, so 250. Second method, I'm going to do like this. Okay, the highest energy of the beta particle, 0.5 mega electron volt, it's losing all its energy. Means it is stopped when it travels through a certain centimeter. I'm not going to find the range here now. I am going to find how many collisions it will make if it wants to lose all its energy. So I can say it's total, the initial energy is 0.5 mega electron volt. So the maximum energy or the highest energy of beta minus is 0.5 mega electron volt. So when it loses all its energy, if it wants to lose all its energy due to collision with nitrogen molecules, how many collisions should it make? During each collision, it will lose 15.6 electron volts. So I can say total number of collision collisions with nitrogen. So 0.5, 10 to the power 6, because it's losing all its energy. During each collision, it will lose 15.6. So how many collisions should it produce? 15.6, if you divide, you will get 3.21, 10 to the power 4 collisions. Right. So that means on its way, the highest the beta particle with the highest energy, if it wants to lose all its energy, it should make this number of collisions with nitrogen molecules. So that means it should meet this number of nitrogen molecules. Okay, we don't know the range. We are going to find the range. Now, we know that 250 collisions will be produced in 1 centimeter. So I can say 250 collisions will be produced in 1 centimeter. In 1 centimeter. So this number of collisions, how much distance should it travel to produce such collisions? So number of collisions, so the distance traveled or the range is equal to, if it wants to lose all its energy. So 250 collisions in 1 centimeter means over 250 into 3.21 10 to the power 4. You will get 128.4 centimeter, that is 1.28 meters, approximately 1.3 meters. So the range is 1.3 meter. Now check it with the second graph. Check it with the second graph. For 0.5 mega electron volt, the range is 1.3. I calculated the 1.3. Am I getting 1.3? Yes, we will get 1.3. So this is the calculated value, right? So check this value. With the range given in the second graph. For 0.5 mega electron volt, it tally or it agrees with the value. So the statement is correct. Correct estimation. Okay, question 15 related to cosmology. Procyon is the brightest star in the constellation Canis Minor. The graph shows how the radiated intensity from Procyon varies with wavelength. So actually, radiated intensity against wavelength graph, right? So there's a graph, you know the normal shape. We use the Weed's law. They are giving a graph something like this. Right. A website states that Procyon has twice the diameter of the Sun. Assess the accuracy of this statement. So luminosity given, luminosity of the Procyon given, diameter of the Sun is given. So we need to find the diameter of the Procyon, right? So from this graph, intensity against wavelength, we can find the temperature by using Wien's law. Then use Stefan Boltzmann equation, L equals sigma A T to the power 4, and find the diameter of the Procyon. Then divide that diameter by the diameter of the Sun, whether we are getting 2 or some other value. We'll check it. So simple equation, normal question, right? So I can say from the graph, so that graph, we can say lambda max, that will be 450 into 10 to the power minus 9 meters or 450 nanometer. The x-axis is given in nanometer, 10 to the power minus 9 meter. So use Wien's law, that is lambda max into T equal 2.898, 10 to the power minus 3. Substitute the value 450 10 to the power minus 9 into T equal 2.898 10 to the power minus 3. From the T, the peak, the surface temperature that we can find it. So that will be 6440 Kelvin. Okay, so now I'm going to use Stefan Boltzmann equation. L equal sigma A T to the power 4, and we know A is equal to 4 pi r squared or d by 2 all things squared. D is the diameter. So I'm going to find the diameter of the procyon. So I know the luminosity given, that is 2.65 10 to the power 27. Stefan Boltzmann constant, that is 5.67 10 to the power minus 8 4 pi d by 2 squared into T to the power 4. Temperature, we know that 6440. So find the D here. Solve it. D will be equal to 2.94 10 to the power 9 meters. So that is the diameter of the procyon. So find diameter of the procyon divided by diameter of the sun, that is 2.94 10 to the power 9. Diameter of the sun is given as 6.96 10 to the power 8. So you will get that is 4.23, that is greater than 2. So the question is, assess the accuracy of this statement. They say the statement is the procyon has twice the diameter of the sun. No, that is almost 4 times the diameter of the sun. So you have to show this and say it is not twice. You can write finally, it is not twice the diameter. The diameter of the procyon is actually not twice the diameter of sun, almost 4 times the diameter of the sun. You should write it here. Okay, question 16 is about about gravitational motion. This image is given saying that represents our galaxy, the Milky Way. Astronomers think that there is a very large concentration of stars in the central region. So when you think, when you consider galaxy, in most of the galaxies, the most of the stars will be concentrated at the center called nucleus of the galaxy. And you know, all galaxies, all the stars in galaxies are moving in spiral path or circular path, we can consider, around the nucleus. So the nucleus consists of most of the stars of the galaxies, and some of the stars are distributed outside the nucleus of the galaxy. So we can assume most of the mass of the galaxy is concentrated within the nucleus. So when we think about an enclosed sphere, say when we think about the mass enclosed within a virtual sphere, say for example, when we think about the mass somewhere, if I think about a virtual sphere around this nucleus somewhere here, the total mass enclosed within this sphere, total mass enclosed within this sphere will be same as the mass inside the nucleus, because other mass here is normally, all the mass due to visible stars will be negligible compared to the mass concentrated within the nucleus. There's a law called Gauss law, not in the Edexcel syllabus. Gauss law says the gravitational force, when you think about the gravitational force or gravitational effect, calculate F equal G m1 m2 r squared or G equal GMO r squared, where mass is the mass enclosed within the virtual sphere we consider. For example, I'll think a little bit, I'll briefly tell about the this meaning of word, the enclosed mass. Say for example, when you think about Earth, the mass of the Earth, if I say m, The gravitational field strength on the surface of the Earth, if I say the radius of Earth is R, the gravitational field strength on the surface of Earth is given by G equal Gm over R squared. Okay, so where M is the total mass of the Earth, we assume it is concentrated at the center of mass. But if you want to find the gravitational field strength inside the Earth, somewhere here, inside the Earth, somewhere at point P, what will be the gravitational field strength? There I can't write Gm over R squared, I can't write. Where the reason is, R you can consider this R, but mass you can't substitute the whole mass of the Earth, because we need to consider the mass enclosed within a virtual sphere that has radius R. So we need to find the mass enclosed within that virtual sphere, that is the Gauss law. We need to consider the mass enclosed within this virtual sphere. So I can assume the Earth is uniform, uniformly distributed distribution of mass. So I can say the mass, the whole mass of the Earth, if I say m, that is equal to due to 4 by 3 pi r cube, that's the volume of the Earth, into density. So I can find the density of the Earth in terms of r cube. So density of the Earth will be 3 by 4 m over rho. I can say rho is the uniform distribution of the density, uniform distribution of, I can consider it as a density of the Earth. Then I need to find the mass in, r cube, sorry, for 3 by 4, 3 by 4 m over pi r cube. So I can find the mass enclosed within the sphere of radius r, that I can find it in terms of capital M and capital R. That is going to be 4 by 3 pi r cube into 4 by 3 pi r cube into the density. So that is 3 by 4 m over 4 m over pi r cube. So that will be 4 and 4 will get cancelled, 3 and 3 will get cancelled, pi and pi will get cancelled. So that is m r cube over r cube. That is the mass enclosed within this virtual sphere that has radius symbol r. Now I can say the gravitational field strength inside the Earth at point P is given by G equal Gm, this m, over r squared. So I can say G, instead of m, I can substitute m r cube over r cube over r squared. So that is going to be G m over r cube times r. Okay, so that's the way the gravitational field strength inside the Earth varies with distance from the center. When it comes to the surface, the whole mass will be enclosed within that sphere. This all related to Gauss law. So I can say the gravitational field strength inside the Earth, if I draw the graph for G against the R, until it comes to the radius of the Earth, R, the G proportional to R, so the graph will be like this. So the gradient is a straight line. Then it will decrease from the outside, it will decrease exponentially. That's a graph for that. Okay, so some type of idea we are going to use in this question also. Okay, so this question says, astronomers think that there is a very large concentration of stars in the central region of the galaxy. Outside this central region, the concentration of stars is very much less. I already explained that. All the stars in the galaxy are rotating about its center. It can be shown that the velocity v of the star, a distance r from the center of the galaxy, is given by this equation. You know that we learned that in gravitational field, circular motion and gravitational field. Where m is the mass of the galaxy contained, means enclosed in a sphere of radius r. So that's the Gauss law actually. Now they are giving a graph, they are giving a graph something like that. How the speed varies with r, they are giving a graph like this. A graph is given like this. Explain how the expression gives the variation of V with R shown by the graph. Okay, so you can say like this. When we consider the nucleus, so when we think about R starting from 0, so here R is starting from 0. So within the nucleus, we can say the mass is directly, if I assume the density is constant, the density of the distribution is constant, I can say mass is directly proportional to R cube. So I can show like this. Okay, so within the central region, since most of the mass is concentrated of the galaxy, and we can assume the density of the central region of the galaxy is constant, we can find the mass enclosed within the central region of the galaxy is given by 4 by 3 pi r cube rho. So V equals square root of gm over r, they are given. So G, the mass is substituted over r. So r cube here, r, when you solve, it will be now G is constant, 4 by 3 pi is constant, rho is constant. R cube over r is r squared within the square root. So square root of r squared is r. So we will get G equal square root of 4 pi G rho times R, that is V directly proportional to R. This is true only up to the radius of the central region or up to the radius of the nucleus. So up to the radius of the nucleus, central region of the galaxy, speed will increase almost like a directly proportional relationship. So speed will increase. So that's the reason the graph is given something like increasing speed. So the graph is given like this way, increasing speed, almost straight line. Yeah, like increasing speed, they are giving the graph something like this. Now, when it comes to the radius of the nucleus, that will be the maximum. Until that, it will increase. So at the radius of the central region, the maximum speed will occur. Then when we go out of the central region, there is no significant change in mass because most of the mass is concentrated within the nucleus. So when we go outside the nucleus, there is no change in mass, but radius is increasing. So according to V equals square root of gm over r, no change in m, but r is increasing. So V will be directly proportional to almost 1 over square root of r. So the graph will decrease. So the speed will decrease. So what I explained in the previous part, the graph given by in the exam paper in the previous part is the actual expected graph. The graph should be like this because since most of the mass is concerned at the nucleus of the galaxy, the speed should increase then decrease outside the nucleus. The speed should decrease because most of the mass is concerned at the center. We already explained that. But practically, when they measured the speed of the stars around the galaxy, this is the observed speed. There is no significant drop in the speed. It remains almost constant speed even when you go outside the nucleus of the galaxy. The question is, suggest why the observed velocity varies as shown. So 2 mark question. The answer should be, now, actually, what we expected when R increases outside the nucleus, we assume the mass remains constant inside the nucleus. That's the thing we expected. But what is happening actually, even when the outside the nucleus, when we consider a distance which is more than the radius of the nucleus, there is invisible mass exists. There is mass also increasing. When R increases, according to V equals square root of gm over R, so most of the mass is considered within the nucleus means when you move outside, when you consider outside the nucleus, when R increases, M is remaining constant. So we told in the previous part, V is directly proportional to square root of 1 over R. But what is happening here? Actually, there is some invisible mass. Even when we consider outside the nucleus, there is no change in M. So mass also, when we consider outside the nucleus, the mass concentrated within the enclosed within the radius of the sphere is increasing due to invisible mass. So we can say when R increases, mass M also increasing due to invisible matter. Actually, that invisible matter is the dark matter. Okay, question number 16, third part. The ultimate fate of the universe may be a closed universe, but astronomers cannot be sure what their current model predict. Explain why astronomers cannot be sure that the universe is closed. Okay, so there we should say 1 mark for saying that. We should say uh, if the universe wants to be closed, then the mass energy density of the universe in future should become greater than critical density of the universe. If it wants to be closed, the gravitational pull should be sufficient to attract all the galaxies towards each other and bring them back. So the first condition we should write, the mass energy density of the universe in future should become greater than the critical mass energy density. Second mark, we can say we can't predict the future mass energy density because when the universe expanding, the mass energy density also will change and there will be larger uncertainty. There will be large uncertainty in the value of mass energy density. So these are the two reasons scientists are unable to predict whether it's going to be closed universe or not. Okay, question 17. A music system has a number of loudspeakers. One loudspeaker produces at low frequency sounds. The loudspeaker consists of a coil connected to a cone. The cone is in a region of magnetic field produced by the permanent magnet. So there is an oscillation happening. Explain how an alternating current in the coil causes the cone to oscillate with the frequency of alternating current. So when a particular frequency of alternating current is connected to a loudspeaker, the loudspeaker will oscillate with the same frequency. Explain how the alternating current in the coil causes cone to oscillate with the frequency of alternating current. So there you can say the when current flows in a coil, there will be magnetic field. So when the direction of when current flows in a coil, there will be magnetic field, and the direction of the magnetic field produced by the coil will change at the same frequency as the AC current. So if the frequency of the current is 50 hertz, the direction of the magnetic field produced in the coil also will change every 50 seconds, every 50 times per second. So you can say direction of the magnetic field created by the current in the coil will change continuously at the frequency of the alternating current. So this magnetic field interact with the magnetic field produced by the permanent magnet and there will be force acting on the coil. So the direction of the force also will change at the same frequency as the frequency of the alternating current. Therefore, the cone is connected to the coil, so the cone will oscillate at the same frequency as the frequency of the AC current. Is the A part. Okay, question number 17B part, first part. A signal of constant frequency is applied to the loudspeaker. The coil moves with a simple harmonic motion. Loudspeaker emits sound of frequency 75 hertz. When the loudspeaker is producing this sound, the coil moves through a maximum distance of 3.5 millimeters. So maximum distance of 3.5 meter means that is between the extreme positions. That's the maximum distance. Say for example, the coil is oscillating from this position to this position. This maximum, this is 3.5 millimeter. So that means the equilibrium position will be at the center. So the amplitude of the oscillation will be half of this. So the amplitude will be half of 3.5 millimeter. That is the amplitude. Okay, so the question is find the maximum speed of the coil. We know that V max equal A omega. So amplitude is 3.5, 10 to the power minus 3 divided by 2. That's amplitude. I already explained that. In omega, 2 pi f. So we know that omega equal 2 pi f. We know the frequency, that is 75 hertz. So that will be 0.83 or 0.825 meter per second. Second part of the part, state the position where the velocity is maximum. We know that is the equilibrium position, center of extreme position. Center of extreme position is the equilibrium position. So the 1 mark question, the answer is equilibrium position. C part, at a particular frequency, loudspeaker cone starts to oscillate with a very large amplitude. Explain why this effect observed. So you can see energy is transferred from the coil to the cone at a particular frequency. The natural frequency of the cone and the frequency of the coil becomes the same, or you can say at a particular frequency of the coil, its frequency becomes equal to natural frequency of the cone, natural frequency of oscillation of the cone. Therefore, maximum amount of energy will be transferred from the coil to the cone and resonance will occur. Again, I'm telling, at a particular frequency of oscillation of the coil, that frequency will be equal to natural frequency of oscillation of the cone. So maximum amount of energy will be transferred from the coil to the cone due to resonance. That's the reason cone will oscillate with larger amplitude. That's the answer for C part, question number 17. Okay, question number 18 about planetary motion based on Kepler's law. So the equation is given T squared equal KR cube. So the question A part, the table shows data for Earth and Mars. So they are giving the time period of circular motion of the Earth around the Sun and Mars around the Sun. Also the distance of the Earth from the Sun and distance of the Mars from the Sun, all are given on a table format. Show that for Earth and for Mars, K has the value about 3 into 10 to the power minus 9. So nothing, just substitute in this equation, very basic question. So I can say for Earth, I'm answering A part. So Earth, I can say K is equal to T squared over R cube. T squared is equal to 3.16 10 to the power 7 all things squared over. So K equal 3.16 10 to the power 7 divided by 1.50 all in cube. So that will be 2.96 10 to the power minus 19 seconds squared. That's a time unit. M to the power minus 3. Same way, if you do it for, so this is approximately equal to 3 into 10 to the power minus 19 s squared m minus 3. Same way, do it for mass. K is equal to 5.93 10 to the power 7 all things squared divided by 2.28 10 to the power 11 all things cube. So that will be equal to again 2.97 10 to the power minus 90 second squared m minus 3. Sorry, yeah, m minus 3. So approximately same thing, 3 into 10 to the power minus 19 s squared m minus 3. Okay, B part, Kepler's law of harmonic was derived by using Newton's. Anyway, they are saying determine the value of K by applying Newton's law of gravitation for a planet of mass m moving in a circular path. Mass of the sun is given. So we need to find the value of K by using Newton's law of gravitation. So we know that F equal G m1 m2 r square, F equal G mass of sun, mass of the planet over r square. That will be the centripetal force, mr omega squared. And we know omega equal 2 pi over t. So m and m will get cancelled. So g ms over r cube equal omega squared. I can say 2 pi over t all things squared. So that will be 4 pi squared over t squared. Make the t squared subject. T squared equal 4 pi squared over gm times r cube. So here this is going to be k according to the earlier equation. T squared equal k gm I can say. So t squared equal k r cube. So k will be equal to 4 pi squared over gm. Find the value of k. So 4 pi squared over g given on the data sheet 6.67 10 to the power minus 11 into mass of the sun is given ms. Mass of the sun is given, that is 1.99 10 to the power 30. So when you solve, you will get the value of k here. That will be 2.97 10 to the power minus 19 second squared m minus 3. Okay, question 18, part C. Jupiter is the most massive planet in the solar system and has many moons. Kepler's law of harmonic applies to the orbiting moon. So they are saying uh, Ganymede is Jupiter's largest moon. Ganymede has an orbital radius given 1.07 10 to the power 9 and the orbital period given 172 hours. Another moon, Io, has an orbital radius 4.22 10 to the power 8 meter. Calculate the orbital period T1 of Io around the Jupiter. So we can use the equation T squared equal K R cube. So I can say for Ganymede, so t squared is equal to 172 hours equal k into r cube is given 1.07 10 to the power 9 all the cube. I can take it equation 1. Then for the IO, T1 squared equal k into r cube 4.22 into 10 to the power 8 all the cube. So to find the T1, divide 2 by 1. Simple equation. So find T1. That will be 42.6 hours. Okay, question number 19, A part. So they are saying about using parallax measurements. Astronomers can determine distance to all stars with parallax angle. This is the parallax angle. Parallax angle greater than 2.4 10 to the power minus 17 radians. Because if the parallax angle becomes smaller, that means when the distance increases, parallax angle will become smaller. The instrument won't be able to measure that angle. So if the angle is greater than 2.4 10 to the power minus 7, the distance could be measured by using parallax method. So there the given data, the distance from the earth to the sun is given 1.5 10 to the power 11, and the distance of a star, that is a Cepheid alpha star alpha Cepheid is 4.6 10 to the power 17 from the Earth. I need to find the angle theta. So here you can say sine theta. This is question number 19a part. I can say sine theta equal opposite, that is 1.5 10 to the power 11 divided by 4.6 10 to the power 17. So if you keep your calculator in radian mode, solve it and find the angle theta, you will get it in radians. So you will get 3.26 10 to the power minus 7 radian. So your calculator should be in radian mode. So 3.26 10 to the minus 7 radians. So that is greater than, this angle is greater than 2.4 10 to the power minus 7 radian. So you can measure distance of this particular star by using parallax method. Okay, question number 19, B part. Cepheids are type of standard candles. Describe how standard candles can be used to determine distances to stars. So it's a very common question repeated several times again and again. So you can say like this. These are the answers. So what is standard candle? Better say standard candle is a star with known luminosity. So we must know the luminosity of the standard candle. First mark, you will get it. Second, you should say measure the intensity or radiation flux of the standard candle from the earth. Second mark. Then by using I equal L over 4 pi d squared, the distance can be measured. Third mark. Okay, so question number 19 C part, a chart diagram is given. So LOL not, and they asked to name the first part of question number 19 part C, first part. Label the x-axis, so that is temperature, and they ask to include a scale. You should include approximate values, and they said in the question Z3 is sun. The sun is yellow star, a surface temperature of 6,000 Kelvin. In the 20th century, astronomers discovered. So Z3 is almost 6,000. So you can mark somewhere here 6,000. So this is, you can mark 12,000, and this one you can say 3,000. Normally equal division, so equal ratio. So 12,000, 6,000, 3,000. So there are 5 zones. That's the second part. Z1, Z2, Z3, and Z4 and Z5 identified on the chart diagram. Complete the following table. So high mass hot stars. High mass hot stars means they are main sequence stars. So high mass hot stars. So even white dwarf is hot, but their mass is not that high. So high mass hot stars are the main sequence stars. They are O group stars, that is Z1. So the table high mass hot stars zone is Z1. Low mass cool stars. Low mass cool stars. So actually they are cooler means okay, could be red giant, but they are not low mass. So low mass cool stars also should be main sequence, that is Z5. Then low mass hot stars, low mass but hot star means it should be a white dwarf, Z2. So these are the answers. You should give it in the table. Third part, explain how a star like sun evolves as its progress from zone Z3, that is the main sequence, to final position in a chart diagram, so that you can find in any textbook, you know, when it is in the main sequence, outward radiational pressure will be balanced by inward gravitational pressure, and hydrogen fusion will occur in its core. So when the hydrogen fusion is completed, core will be occupied by helium and the hydrogen will occupy the outer layer. So inside the core, the temperature is not enough, so no further fusion reaction. So the core will contract due to inward gravitational pressure because no outward radiation pressure, no fusion. Star will leave the main sequence. So now when it is contract, the temperature will increase. When the temperature increases, helium fusion will start and the helium fusion will become significant. So due to the outward radiational pressure given out by the helium, the outer layer of the star will expand. When it expands, its temperature will decrease. According to Wien's law, the temperature decreases will cause its peak wavelength to increase. So it will become red and a larger size. That will become red giant. When the fusion in the core is now helium. When it becomes significant, what will happen? The star is unable to withstand to the outward radiational pressure, so it will explode and throw away the outer layer, and then it will form planetary nebula. After planetary nebula is formed, no further fusion reaction. So due to inward gravitational pressure, the core remnant will shrink a lot and the temperature will increase and the star will become white dwarf. So that you can see in any textbook. So I'm not writing the answer. All of you know that. So that is the answer for question number 19, part C3. Okay, question number 20. Reaction equation is given and they asked to balance it. So it's an alpha emission of actinium that's becoming francium and alpha particle. So they asked to balance this reaction equation. Alpha 42 we must know. So balance it. This will be 87. This will be 221. Okay, B part. In a radiative decay, energy is released and the total mass decreases. Show that the energy released if the mass decreased by 1 U is 930 mega electron volt. So the B part we can say delta M is 1 U means 1 into 1.66 10 to the power minus 27 kilogram. 1 U equal 1.66 10 to the minus 27 kilogram given in the data sheet. So the energy release E equal delta M times C squared. So 1.66 10 to the power minus 27 into 3 into 10 to the power 8 all things squared. We'll get it in joules. But they asked to show that in mega electron volt. So to convert to mega electron volt, divide this by 1.6 10 to the power minus 90, we'll get it in electron volt. To convert to mega electron volt, 10 to the power 6 divide again, that will be mega electron volt. Now solve it, you'll get the answer 933.8 mega electron volt, approximately 930 mega electron volt. Okay, so C part, the francium nucleus and the alpha particle move away from each other after decay. So that means we know that before decay, actinium is at rest, so its momentum equal to 0. So they are moving in opposite direction to conserve the momentum. But we know that momentum of francium will be equal to momentum of alpha in terms of magnitude. They have the same magnitude of momentum in opposite direction because initial momentum of actinium is 0 and the total momentum is conserved. So explain why the kinetic energy given to the alpha particle is just less than 5.9 mega electron volt. Mass decrease for the decay. So in this decay, the mass deficit is 6.35 10 to the power minus 3 U. So C part, they are saying delta M equals 6.3235 10 to the power minus 3 U. And already we found it. If there's a mass deficit of 1 U, the energy release will be 933.8 mega electron volt. So the energy release in this decay will be equal to 6.35 10 to the power minus 3 into, if 1 U decay happens, we already found it, that is 933.8 mega electron volt. So that will be equal to 5.93 mega electron volt. So this is the total energy released in the form of kinetic energy of francium and alpha particle. So we know that kinetic energy of alpha plus kinetic energy of francium will be equal to 5.93 mega electron volt. So how much will alpha get, how much will francium will get? That depends on their mass actually. You know, momentum is conserved, and I told these two will have the same magnitude of momentum in opposite direction. And we know that kinetic energy equal p squared over 2m. So instead of this one, I can say p squared alpha over 2 times mass of alpha plus p squared fr over 2 times mass of fr, that is equal to 5.93 mega electron volt. But the numerators are the same because they have the same magnitude of momentum. So we know that mass of alpha is much smaller than mass of francium. Almost, you know, the mass of francium is 221. If I take mass of alpha is 4 units. So almost mass of alpha is 55 times smaller than mass of the francium. So if I consider the ratio of kinetic energy of alpha over kinetic energy of francium, that will be equal to p squared alpha over 2 times mass of alpha times 2 times mass of francium over p squared francium. But p squared alpha, p squared francium have the same magnitude in opposite direction, so they will get cancelled. So 2 and 2 will get cancelled. It's going to be mass of francium over mass of alpha. So I can say, I'll continue here, kinetic energy of alpha over kinetic energy of francium will be equal to mass of francium over mass of alpha. If I think in terms of mass number or the nucleon number, that is 221 over 4, because you know we can take mass of proton and mass of neutron have the same magnitude of masses. So the mass of francium to mass of alpha will be ratio of mass number. So that will be approximately 55. That is, kinetic energy of alpha will be 55 times the kinetic energy of francium. So the total energy release is 5.93 mega electron volt. That will be divided across the alpha and francium at the ratio of 55 is to 1. So most of the energy will be obtained by the alpha particle. Okay, so last question, question number 20, part D. The activity of a sample of actinium is 7.4 10 to the power 7 BQ when it is prepared. Calculate the number of actinium atom in the sample 7 days later. Half-life is given as, half-life of actinium is given as 9.9 days. So D part, question number 20. So we know that T half equal ln2 over lambda. So lambda will be ln2 over half-life is 9.9 days. So that will be, I can convert to seconds. So because I'm going to use a equal lambda and I should convert to second, then it will be easier later. I can use the same lambda. So 9.9, 24 into 60 into 60. If I want to convert to second, 9.8, 1 day 24 hours, 1 hour 60 minutes, 60 seconds. So that will be 8.10 10 to the power minus 7 per second. That's the value of lambda. So we know that the activity after 7 days, so A equal A naught e to the power minus lambda t. So currently the activity is 7.4 10 to the power 7 e to the power minus lambda is 8.10 10 to the power minus 7 into after 7 days. So I need to convert 7 days into seconds, 7 into 24 hours, 60 minutes, 60 seconds. Solve it. The activity after 7 days will be 4.53 10 to the power 7 becquerel. If you are using A equal lambda in later, lambda must be in per second. So that's the reason I found the lambda in per second already. So I know the activity 4.53 10 to the power 7 equal lambda 8.10 10 to the power minus 7 times n. Find the n. 5.6, 10 to the power 13. So that's the number of radioactive particles of actinium after 7 days. Okay, so that's the end of this paper discussion. I hope you understood.